Calculating kilovolt amps, wire size, and overcurrent protection for a motor circuit involves several steps, referencing the National Electrical Code, or NEC. Here's a breakdown. Firstly, to determine the kilovolt amps, or kVA, for a motor on a panel schedule, you use the formula kVA equals voltage times current times the square root of 3 divided by 1000. In this case, the voltage is 208 volts, and the current, or minimum circuit ampacity, is 40 amps. Since it's single phase, we assume the square root of 1. Therefore, kVA equals 208 volts times 40 amps times the square root of 1 divided by 1000, which equals 8.32 kVA. This calculation provides the kilovolt ampere rating, which is essential for panel schedule planning. Secondly, determining the appropriate wire size for the motor circuit requires consulting NEC Table 310.16. This table provides guidance based on the ampacity of the conductors and their insulation temperature rating. Assuming a 75 degrees Celsius insulation rating for a 40 amp load, Table 310.16 typically recommends number 8 AWG copper wire. This selection ensures that the wire can safely handle the motor's current without overheating, provided all conditions meet the table's specifications. Thirdly, determining the overcurrent protection, or OCP, involves understanding NEC Section 430.52, which provides guidelines for motor circuit protection. This section stipulates that the overcurrent protection should not be less than 125% of the motor's full load current rating for continuous duty motors. If the motor has a minimum circuit ampacity of 40 amps, the minimum overcurrent protection allowed is 125% of 40 amps, which equals 50 amps. Regarding the breaker size, it's common practice to select a breaker that's higher than the minimum overcurrent protection to provide a margin of safety and prevent nuisance tripping. In this scenario, a 60 amp breaker would be a suitable choice. Alternatively, a fuse could be used, but it would need to be rated at 50 amps. It's important to note that these calculations and selections should always be verified by a qualified electrician or engineer to ensure compliance with all applicable codes and standards. The motor's nameplate should be consulted for its full load amps, or FLA, which is different than the minimum circuit amps. The FLA is the actual current the motor draws under full load conditions. The minimum circuit ampacity includes a safety factor to account for starting currents and other potential overloads. When selecting the overcurrent protection device, you need to consider both the NEC requirements and the specific characteristics of the motor. Some motors may require additional protection, such as thermal overload relays, to prevent damage from overheating. It's also important to ensure that the overcurrent protection device is properly sized for the wire gauge used in the circuit. An undersized overcurrent protection device may not provide adequate protection, while an oversized device may allow the wires to overheat and potentially cause a fire. Always consult the NEC for the latest requirements and guidelines for motor circuit protection. The NEC is updated regularly to reflect changes in technology and industry best practices. The NEC provides specific tables and formulas for calculating wire size and overcurrent protection based on various factors such as motor horsepower, voltage, and operating conditions. In addition to the NEC, local codes and regulations may also apply. It's important to check with your local building department or electrical inspector to ensure compliance with all applicable codes. Proper motor circuit protection is essential for ensuring the safety and reliability of electrical systems. By following the NEC guidelines and consulting with qualified professionals, you can ensure that your motor circuits are properly protected from overcurrents and other potential hazards. Remember that electrical work can be dangerous, and it's always best to hire a qualified electrician to perform any electrical installations or repairs. Never attempt to work on electrical systems unless you are properly trained and qualified. Taking shortcuts or ignoring safety precautions can lead to serious injury or even death. When selecting wire, consider not only the ampacity requirements but also the environmental conditions in which the wire will be installed. Factors such as temperature, moisture, and exposure to chemicals can affect the performance and lifespan of the wire. Choose a wire that is specifically designed for the intended application and environmental conditions. Also, consider the voltage drop in the circuit. Voltage drop occurs when the voltage at the load is lower than the voltage at the source due to the resistance of the wires. Excessive voltage drop can cause motors to run inefficiently and can even damage equipment. To minimize voltage drop, use larger wire sizes or shorten the length of the circuit. When selecting overcurrent protection devices, consider the interrupting rating of the device. The interrupting rating is the maximum amount of current that the device can safely interrupt. Choose a device with an interrupting rating that is sufficient to handle the available fault current at the installation location. Also, consider the type of overcurrent protection device. Fuses and circuit breakers are the two most common types of overcurrent protection devices. Fuses are typically less expensive than circuit breakers, but they must be replaced after they trip. Circuit breakers can be reset after they trip, but they may be more expensive. Choose the type of device that is best suited for your application and budget. When installing overcurrent protection devices, follow the manufacturer's instructions carefully. Improper installation can compromise the performance and safety of the device. Also, ensure that the device is properly labeled with its ampacity and interrupting rating. Regular inspection and maintenance of motor circuits are essential for ensuring their continued safety and reliability. Inspect the wires, connections, and overcurrent protection devices regularly for signs of wear, damage, or corrosion. Replace any damaged or worn components immediately. Also, test the overcurrent protection devices periodically to ensure that they are functioning properly. Proper documentation of motor circuits is also important. Keep accurate records of the wire sizes, overcurrent protection devices, and other components used in the circuit. This information can be helpful for troubleshooting problems and performing maintenance in the future. Remember that electrical codes and standards are constantly evolving. Stay up to date on the latest changes and ensure that your motor circuits comply with all applicable requirements. Consider attending training courses or seminars to learn more about motor circuit protection and electrical safety. There are many resources available to help you stay informed and compliant with the latest codes and standards. Working with electricity can be dangerous, but by following the proper safety precautions and consulting with qualified professionals, you can minimize the risks and ensure the safety of yourself and others. Always prioritize safety when working with electricity. Never take shortcuts or ignore safety warnings. If you are unsure about any aspect of motor circuit protection or electrical safety, consult with a qualified electrician or engineer. Their expertise can help you ensure that your motor circuits are properly designed, installed, and maintained. Do not forget that safety is always the most important factor when dealing with electrical systems. By following the steps outlined and seeking professional help when needed, you can ensure the safe and reliable operation of your motor circuits. Let's recap the key steps for determining kVA, wire size, and overcurrent protection for a motor. 1. Calculate the kilovolt amps using the formula kVA equals voltage times current times the square root of 3 divided by 1000. 2. Determine the appropriate wire size by consulting NEC table 310.16 based on the ampacity and insulation temperature rating. 3. Determine the overcurrent protection by following NEC section 430.52, ensuring it is not less than 125% of the motor's full load current rating. 4. Select a breaker size that is higher than the minimum overcurrent protection for a margin of safety. 5. Always verify the calculations and selections with a qualified electrician or engineer. 6. Consult the motor's nameplate for its full load amps, which is crucial for accurate protection. 7. Consider additional protection such as thermal overload relays for motor safety. 8. Ensure the overcurrent protection device is properly sized for the wire gauge. 9. Stay updated with the latest NEC requirements and guidelines. 10. Check with local codes and regulations for compliance. By carefully following these steps and prioritizing safety, you can effectively manage motor circuit protection and ensure the longevity and safety of your electrical systems. Understanding the principles behind these calculations and code requirements is essential for anyone working with electrical systems. It empowers you to make informed decisions and contribute to a safer working environment. Always remember that electrical work requires precision and attention to detail. Double-check your calculations, verify your selections, and never hesitate to ask for help when needed. Your expertise and diligence are crucial for maintaining the integrity and safety of electrical installations.